Well, hello everyone. Welcome to the next Blue Waters webinar. My name is Maxim Belkin. I'm an education and training coordinator in the Blue Waters project at the National Center for Supercomputing Applications. Today's webinar is by Shantanu Cha and Ioannis Paraskivakos from the Rutgers University. Professor Cha is an associate professor of electrical and computer engineering, and Ioannis is a research assistant in Professor Cha group. We have two members of Professor Cha group in the Slack channel, so please feel free to ask questions during the webinar. And with that, I'll turn it over to Shantanu.
Thank you. Thank you very much. And good morning, everybody. It's a pleasure to be presenting and talking about RADICAL-Cybertools as part of the Workflows webinar series. Thank you to the Blue Waters team, and thank you very much to Scott and his team for making this possible. Today, the format's going to be a 15 to 20 minute introduction about RADICAL-Cybertools to orient everybody about what it is that we're trying to develop and how this is an important addition to the landscape of existing workflow tools. But we'll very quickly move away from talking about RADICAL-Cybertools to actually doing things with RADICAL-Cybertools. And this is where I'll be ably assisted by Ioannis, who's physically co-located with me, but also at least two other people on the Slack channel. So as was pointed out, please do, as you get on to the hands-on, feel free to ask questions if we're not clear at any stage. On the very slide that you should see right now, you'll see links to both the group's webpage, but also a starting point for the software that we will be talking about. Next slide, please. Oops. Okay. Sorry. So let's ask a question, which is, why is it so difficult to build scalable, extensible, and flexible workflow tools? And I'm going to ask this question in the context of workflow tools, but hopefully the questions resonate for tools, software tools in general in support of computational science. There are many arguments, many reasons, but I'll focus on three with the hope of motivating RADICAL-Cybertools. The first and foremost is that every HPC system, high-performance computing system, and environment is different. If not actually unique, whether it be the software environment or the middleware environment, or whether it be the set of libraries. And incorporating this extreme heterogeneity is a non-trivial task, and creating the tools, the abstractions that can insulate tools, end-user tools from this is quite a challenge. However, another interesting observation, which many of you, I hope, will agree with, is the fact that historically high-performance computers have been designed and optimized for single large jobs. And this is quite understandable. But both from an applications point of view as well as from a technology point of view, it's important to appreciate that this will no longer be true and will, in my opinion, become increasingly less true, i.e., there will be a need to support many concurrent job tasks by a user as part of a larger, let's say, workflow. And as things stand right now, because this is a shift from the historical use of high-performance computers, we find ourselves in a window where there are arguably missing abstractions, gaps in existing capabilities, when you're trying to, as a single user, run applications or workflows that have more than one concurrent executing tasks. And the gaps are at many levels. There's obviously the programming interface and the coordination, but there are also gaps in how the resources for these multiple tasks, which are the bedrock of workflow systems, is provided. So the third reason is the tension between having a general purpose solution versus a specific solution. Whether you look at this from a performance versus portability issue, or whether you look at it from the point of view of how quickly can I get started for the application that I'm interested in, versus the tension of learning a new system. So if you already know a tool, it's much easier to try to get to use it. But what if that tool doesn't meet all your requirements? So there's this tension which exists at many different levels for many different tools. But in workflow systems, as a consequence of the first 2 points, this tension is somewhat exaggerated and increased. Next slide, please. And this is why, as an academic endeavor, we, over the past several years, have been thinking about building blocks for workflows. And I will take a few minutes to try to give you the context of this research agenda, and then quickly transition into describing an incarnation of this research agenda. So the first point is that workflow systems were initially developed for very large projects such as the Large Hadron Collider, projects such as gravitational wave detection. And with these big science projects in mind and the structure of these big science projects, workflows were constructed such that there would be a bunch of specialists to support a workflow which would then be used by hundreds, if not thousands, of scientists. So there was a workflow or a few workflows used by hundreds or thousands of scientists. That ratio is very important. Also, over the past decades, the infrastructure has been evolving. And although it still may appear fragile and unreliable to some, I can assure you, having been in the field for a decade or a few decades, it's nowhere near as fragile as it used to be. So when you think of how workflows came about, it was for these large projects with the limited ability of general purpose infrastructure. And that's where a lot of these workflow systems were originally introduced. So things have changed. Now workflows are no longer used by large science projects, and the infrastructure, although still slightly unreliable, is not as unreliable as it ought to be. If you think about the generalization of workflows to no longer just being the domain or preserve of big science, you now have many individual PIs, small groups, trying to use workflow systems. And therefore the design point that I roughly alluded to of one workflow fitting a large number of researchers no longer holds. And this requires a fundamental rethink of the way workflow systems are designed. So you will notice I'm toggling between workflows, the application, and workflow systems as the tools used to execute to manage these workflows. And consistent with an earlier observation, a lot of these workflows and applications are based upon single tasks which may have different levels of coupling, or they may be entirely independent. So in a nutshell, the point really that you should appreciate is that workflows aren't what they used to be for a whole set of reasons. Moving from the conceptual to, let's say, a more tools-oriented approach, it's also important to appreciate that what is needed is not just workflows for the very end users, but workflow abstractions that can then be used by workflow tool developers, which in turn will be used by the end users. And this chain has to be thought through carefully. And when you think about the changing landscape of workflows and you think about the developers and the crucial role of workflow system developers now, you realize that you need building blocks that will allow quick agile, experimental establishment of workflows as well as production grade. And so it's this, if you will, set of reasons that establish the need for a fresh perspective of workflows. And the specific perspective we're proposing is that you need well-defined building blocks for workflows and workflow systems. Next slide, please. And this is where I move on to talking about RADICAL-Cybertools and how RADICAL-Cybertools actually supports this. But let me take a digression and try to make this less jargony and make this less, if you will, heavy, and try to explain to you what is not really a law in the sense of a law, but are empirical observations. That every tool shims to submit distinct middleware, to submit jobs to distinct middleware as a route of interoperability. Now, this is very possible, but it comes at a heavy cost. And if you think about a corollary to this is that interoperability, instead of being a cross-layer concern, should be provided explicitly and well-defined at the lowest level of possible. And this is the principle of subsidiarity. A second observation is that many application tools eventually grow to become workflow systems. And this, in turn, leads to an interesting corollary that in order to prevent every application from becoming a workflow system, we need to determine what are the common components across workflow systems so that, well, if these components existed and were reliable and robust, then many different workflows, applications would be able to resist the temptation and the technical need to grow into workflow systems. They could do what they know how to do best. Next slide, please. With this worldview, what we typically do is think of 4 different levels. There's the application and the workflow at the very top, the resources at the very bottom, level 4, level 1, respectively. And there are 2 levels, level 3, which we call the workload management. I won't get into the details of distinguishing workflow and workload, but just think of workload as the set of tasks that need to be executed. And the important component is that of the level 2, which we call the task runtime. So the set of tasks that comprise the workflow and what's the runtime system to be used to support these different types of tasks. Okay, and mapping this worldview into a set of components, this is what RADICAL-Cybertools, the different RADICAL-Cybertools does. At the lowest level, we have something called SAGA, which is a standards-based approach to submitting to different job systems and, if you will, cloud systems. At level 2, and this is going to be an important focus of the rest of the tutorial, is what we call a pilot system, Radical Pilot in particular, that is used to abstract resource management capabilities. And independent of the underlying resource, it provides a consistent and a uniform way of thinking of how to manage these the resources in order to run many, many tasks. And this is really the important point, which therefore allow me to re-emphasize that there are building blocks needed to support workflow systems. One particular building block that is used almost universally by all workflow systems because of the fundamental need to support multiple tasks is a pilot system. And what RADICAL-Cybertools does is it allows and provides the opportunity to define a single building block, a single pilot system, which can then be used by many different applications and workflow systems. Next, please. And just so I can give the broader context, as I mentioned, there's a research component, but there's very much a production component. And the cyber tools that I'm referring to, even though I'll focus on the Radical Pilot, it's important to appreciate that they've been integrated with existing tools that some of you will have heard of in the seminar series, Swift, Fireworks, another important material science workflow system, Panda, high energy physics workflow management system. But they've also been used to develop new tools and libraries. In some ways, weak validation, but a validation nonetheless of the building blocks approach for workflow systems. Next slide, please. And this is just a cartoonish way of demonstrating the many different domain science and applications and workflows that have utilized radical cyber tools in different ways. Thank you. So something I won't talk about, but just to make sure we're on the same page. Level 1, if you remember, was about interoperability. The first law of cyber infrastructure is that you need the ability to support interoperability at the lowest level possible, the principle of subsidiarity. The way we do this is through RADICAL-SAGA, and this is an implementation of an Open Grid Forum standard. Next slide, please. Here I'm going to spend some time outlining the concept of a pilot abstraction, and hopefully you'll see why this is fundamentally a very simple way of supporting many different tasks that comprise the overall user application. And that's what you probably see in the upper left-hand corner, an application comprised of, let's say in this case, 7 tasks. So before the concept of pilots was pervasive, what was the traditional way was to take a task and submit it directly to a queuing system. Here we no longer take individual tasks and submit them directly to a queuing system. We now first submit a pilot job, which is really a container job independent of any specific workload. And that pilot job is through possible series of multi-level resource managers, lands eventually on a resource. So next slide, please. And what you see here is the green box, which is the pilot job, an empty job, having been launched and started on the resource and ready to run, but without a workload. So what you've just done is decoupled the acquisition of the resource from the actual workload that's going to utilize that resource. And this concept is very important for workflows because now the workflow has complete control of the resources, but hasn't been bound to determine how to use that resource. And that's the next step, please. So once the resource has been acquired by the workflow system, it can then decide when to submit tasks and importantly, where. So in a nutshell, please, next slide. In a nutshell, what you've really seen of the pilot abstraction is, in addition to the decoupling alluded to, it provides much finer level control of spatial and temporal over the resources slicing and dicing. And you can then build upon this many higher level capabilities, libraries and tools, some of which I alluded to, but importantly, it doesn't have to be a library or tool that was designed to use a pilot system, but even tools that were originally just designed to do it all internally, as in be or integrated end to end. And examples like Swift, Fireworks, and others show the importance of these building blocks. Next slide, please. So what I hope to do is just to try to take this kind of illusion, this schematic that I provided, and give you some more details of the execution. And I'll be very quick in giving you a simplified step-by-step animation. And what I want to just show you over the next few slides, really quickly, is how Radical Pilot actually works and supports, in an interoperable fashion, the assignment of a large number of tasks to different resources without exposing any of the details of the resource to the application or the user. So just really go through this in literally 30 seconds. If you just keep on clicking, I'll try to speak to it. There are many different components of the Radical Pilot system, which are set up in a resource agnostic way. This is a way of making sure that the pilot will have control, or the application will have some level of control of the tasks landing on the resource. If you could continue, please. And these are all just ways of showing the performance, managing the performance. And there are lots of internal details which, as users, you really shouldn't have to worry about, but in ways that enable generality and performance. And the long story in short is a lot of things happen under the hood to ensure that there is a uniform, consistent experience of using the pilot system on different resources without the execution model, without the programming model changing between resources for a given application. And as I said, I don't want to get into the gory details, but this is just a schematic to help you appreciate the many levels of details that have to be handled by a building block such as a pilot. And we may have time at the end to show how this has been used on many different work resources, such as Blue Waters on the one hand, but also clouds as well as other clustering machines. I think this would be a good point to transition to Yanis. Let's leave the Ensemble-Toolkit for later and maybe just start getting hands-on with the pilot itself. Okay.
Hello from me as well. This part of the webinar will be mainly some exercises and how to use Radical Pilot to execute what workload you want with some simple examples and exercises. The first thing that we're going to see is an online example that we have. It doesn't need anything to do from the user to do. And initially, first of all, I have to say that Radical Pilot is written in Python. So you have to use Python and just import Radical Pilot at the beginning as RP in order to be able to use its capabilities. If we run this block of code, what we will see is the version that Radical Pilot has is installed in this specific resource. Now, the example that is going to be executed here is mainly, it's going to create a number of tasks, we call them compute units, and will create all the necessary instances and components of Radical Pilot in order to execute it. The first thing we need to create is a session. A session actually contains all the information about the pilot that are going to be launched and the tasks that are going to be executed on the pilots. On the second line, we create a pilot manager. This is a component that is run on the client side. It manages the pilots. It knows where they lie, which resources locally on an Exit machine on Blue Waters, wherever you have it. The unit manager is again a component that manages the tasks that are going to be executed. We call, as I said before, we call them units. And if we execute this block, we will see the session ID that we have for this execution, as long as the name of the pilot manager and the unit manager. On paragraph 2.2, we're starting creating what we call a pilot. First of all, we have to describe it. And in the description, we have the resource that the pilot is going to be launched. That's usually a label. Local.localhost means your local computer. The runtime of the pilot description is how much time in total the pilot will have the resources that it will ask. Number of cores, how many cores in that resource it's going to use. And then we have to submit that specific pilot description into the pilot manager so that the pilot starts to launch on the resource that it's target, and also submit it to the unit manager so that the unit manager knows that this pilot exists and it can submit units to that specific pilot. So if we execute those commands, we will see that the ID of the pilot is again number 5. The resource is the local machine that this web page lies. The sandbox is the address space of the pilot, and the state of the pilot at this specific moment is pending launch. That means that the pilot has been submitted. It's waiting for it to launch and start being alive in order to execute the task that we want. Next, we're going to describe 2 compute units. Compute units are the tasks that we want to execute. They have several attributes. The most important part are the ones that we see here. Environment setups. So we write the description of a compute unit, and by environment we mean the environment variables that need to exist while that task or unit is being executed. The executable of the unit is the exact program that is going to be executed. In this case, in bin echo. And the arguments are the arguments attribute of the description are the arguments that the executable will get. Finally, we can submit the number of calls for the compute unit. In this case, it's 1. It can be more than 1 in a case of an OpenMP executable or an MPI executable. You can have more than 1 calls, and that will tell the pilot how many cores that specific task needs in order to be executed and to be scheduled correctly. Now, after we have described the compute units, we need to submit those units to the unit manager. And from that point, this is this line here. From that point, the unit manager will find the pilot that those units can be executed and communicate them to that pilot, and they're going to be executed. UMGR wait units, it's a blocking command from the unit manager. It blocks the execution of your initial script in order for all the units that have been submitted until now to be executed. If we execute that one, this is an output that we see. The units are being submitted, they're being executed, and all CUs have completed successfully. And now for the last 2 commands, we're going to print the standard output. Based on the description, because it was a bin echo, it should be I am CU and the number that the CU had as its environment variable. And actually that is what we see. I am CU number 1 and CU number 2. Finally, whenever your script the radical pilot script is being executed, we have to close the session. The session keeps all the information that is needed. If the execution has finished and we don't close the session, that means that the pilots are still going to be alive. They're going to still use the resources and keep the resource that they have acquired in the supercomputer or the resource that you have submitted your execution. So whenever your script finishes, you close the session. That will tell to the pilots that they are not needed anymore, and everything will be shut down cleanly, and the whole environment will be clean, and the resources acquired will be released. This is the most basic example. If we go further, I would like to start showing how things can be done. So, in the under RADICAL-Cybertools, the tutorials repository, there is a wiki page for today's webinar. And if you go to section RP setup, bless you, you're going to see how you can set up Radical Pilot while using GCC and Python. We also support Anaconda Python, at least for the client side. It's not fully supported for the pilot side. What I'm going to do is I have a terminal open. I'm going to copy these commands and run them on my terminal. And as they run, I'm going to tell you what they are doing. I'm sorry. Copy. I'm sorry for that, my terminal dropped. Okay, I have to open it again. It's okay. So here we are. The very first instruction, virtual env, it creates a Python virtual environment. We name it RC examples for this specific tutorial. The second command activates that specific virtual env, and then we start installing RADICAL-Pilot from PyPy. Pip install radical.pilot. It will install RADICAL-Pilot on your virtual env. The fourth instruction copies the examples folder to your home directory, and then we just go in there, and RADICAL-Pilot verbose, the variable we export, will show us a report, a nice looking report that shows how the execution of your RADICAL-Pilot script goes. I have to say, in case the virtual env does not work or you have a problem during RADICAL-Pilot installation, please execute this command. If you don't have Anaconda Python, as far as we know, with Anaconda there is no need to install anything else. Let's hope that everything is being installed. Installation can take a couple of minutes for the very first time, but when that is done and it's finished, you can start working. Now, if we continue through the tutorial and the webinar, first of all, I have to note that whenever we're using a resource, we assume that there is a passwordless SSH connection to that resource, and also there is an SSH config file that gives the username for that specific resource. There is a link provided here that can show you where to go and how to exactly do that. The very first example we're going to execute is going to be executed locally on my laptop that I'm using right now for this webinar. I'm going to get into the specific example and show you what it does and then execute it. But in order to do that, you will allow me to use a second terminal. So examples. And VI00 getting started. Now, before I'm going to execute, I'm going to get you through this specific example. At the beginning, we do the necessary imports for RADICAL-Pilot and RADICAL-Utils. RADICAL-Utils are some utilities that we have built in-house in order to help us with the execution. And as I said during the previous example, the very simple example, the first thing we do in this specific line is we create a session. As soon as a session is being created, we create our pilot manager and our very first pilot description. In this case, the resource is going to be my local host. The runtime is going to be 15 minutes, and we have some extra configurations for your project allocation number, the queue you want to use whenever you're using a supercomputer, the access schema that can be SSH, that can be GSI SSH, for example, and the number, of course, for the pilot. Next, we create that pilot description through the compute pilot description class, and we submit it to the pilot manager. And also, we create the unit manager for that specific session, and we add the pilot to the unit manager. The number of tasks we're going to execute are 128 in total. There is just a simple bin date. And as you can see in this for loop, we create the compute unit description, the description of the tasks. The executable is a bin date. There is no need we don't have a course attribute because it defaults to 1. And after that, we submit the units, wait for them to finish the execution, and in the end, we close the session. And if I am to execute that, going to, excuse me, it's going to look like that. So what we see here is the state where the execution is. We have submitted at this point the pilot is being described and it's been submitted to my local machine, and it's being executed. It created 100 bin date compute units. They're submitted to the pilot manager, and as you can see, it waits for all those units to be executed. A green plus means that the unit succeeded. If it was a red minus, it means that the unit failed. If it was a yellow star, it's an unknown state, so we don't really know what happened. And at the end, we close the session that tells to the pilot manager that the pilot should close and everything is brought down and cleaned up. Also, we print the total session lifetime. This includes the time that your pilots waited in the queue, as well as the total execution time. Now, if I would like to execute this specific example to a supercomputer, in this case, I'm going to use Comet from Exceed in San Diego. I would first of all change this config file. I forgot to say that if you're using Anaconda on your local machine, instead of local.localhost, please use this resource label the same way I'm using the resource label for Comet. And if we go and find Comet or some other machine, we will see that we have a project number, RQ, the schema, and how many calls we're going to take from that. So if I was to run it, Python 00 get started exit.comet. That's probably my mistake. It should actually, for some reason, I don't have connection to Comet right now. We would see the same exactly output, but it would show specifically on Comet. Now, if we move on with radical pilot exercises and actually how to execute those and how to do it, I would like you to go and I would like to walk you through those exercises, what they're doing and how to use them. I'm going to execute them again locally because I don't, for some reason, the computer I'm using to submit it didn't connect directly to Comet. The first example to do is what we call a bag of tasks. This is the simplest type of example. We have a number of tasks completely dependent from each other that we want to execute. In this case, we create a radical pilot script like the one I showed you before with the execution that we want to do. What is being left out of the script, if you want to use it, it's in that folder. We haven't put a resource label, the number of the pilot calls that we're going to use, how many tasks are going to be executed, how big the bug is going to be, and the calls that we need per compute unit. Also, there is an attribute for the queue that's going to be used, and you should also add your allocation number in the pilot description. I'm going to wait for a couple of seconds for if somebody wants to try it by him or herself, and then I'm going to go inside that specific script and do the changes myself to run it locally. In addition, if you're not sure where to find the documents folder, You can download the script from this specific link. Okay. After you have made the changes, you can run that command python simplebot.py. It should start executing the script on the resource you have selected. I also would like to mention that in this wiki page, in case you don't have access to Comet or some other exit machine, there is a link to all which lists all the resources that Radical Pilot currently supports. And you're very welcome to open a ticket for another resource that you may want to support. So if I open simplebot.py, at the beginning you will see the resource label, the pilot course, number, the bug size, and the queue. Because I'm going to use my local computer, I'm going to leave queue to none. But in this case, I would like to increase the bug size to 20. After we create the log report, that's for the report to be as you saw it before, I'm creating a pilot session, a Radical pilot session. And then in this try part of the script, I'm creating my pilot manager, my compute pilot description, and as you can see, the runtime is 30 minutes. So the maximum time that the pilot is going to be alive is going to execute tasks is going to be 30 minutes. Cleanup true means that after you're done, clear the address space that you have used and the queue. In case you're using some specific resource, you should add pilot description dot project here with your allocation number of the resource you're using as a string. After that, we submit the pilot, our pilot to the pilot manager. You start a unit manager and you submit that pilot again to the unit manager so that it knows where to execute tasks. In this for loop, we're creating a number of bineco tasks again. Each task will print that IAMCU number and the number that it has set up in the environment. This is going to create as many compute units as our bug size, that's 20. And then we will submit those units to the unit manager. We're going to wait for them to execute and in the end close the session. The except block here is mainly in order to stop the script and close the session in case something goes wrong or you want to interrupt the execution. I'm going to save this script and then to Python simplebot.py. And I will wait for it to finish. Now, while we wait for the script to finish, in case you want to see where are things happening, there is a folder called Radical Pilot Sandbox. And in there, you should be able to see all the pilots that are being created and be executed. If I go into the last one, that's number 3, you will see that each compute unit has its own folder and also log files that are being created. So I assume that this one has finished. And as you can see at the end, each compute unit was done, correct, it finished correctly. We can see it either from the state or the green pluses here. And all of them printing the actual number. The second exercise example is about chain tasks, and that's mainly trying to explain how to create an execution that has dependencies from one task to another. So in this case, we have a set of tasks A, which can be an echo job again, and then a set B of other tasks that are dependent from task A. So we want to execute tasks B after we have executed the respective task from set A. This specific example is called chain tasks, and it again requires you to make some changes there on the top of the file. You can also download it. And while you do the changes, I would like to walk you through how to create that dependency and chain tasks. So I'm going to open that file. As usual, we have the imports at the top. I'm going to give some time if somebody wants to do some changes, and the resource label, the number of cores, number of chains. That's how many tasks in set A we're going to have, as well as how many tasks in set B we're going to have. CUA executable is the executable that the first set will execute. In our case, it's going to be, for our example, be echo, but can be whatever you want. And also CUB executable is the executable for the second set of tasks. And of course, Q is the key that you're going to use if you want to run this script locally. And if we move down, we'll see again that we create a pilot session. In every Radical pilot script, we create a pilot session. We create a pilot manager for that specific session and a pilot description. And then we submit that specific pilot to the pilot manager. I think it's a good time to note that you don't necessarily it's not necessary to have only one pilot. You can add as many pilots as you want to your script through additional descriptions and submit them to the pilot manager, and those pilots will be executed. Then we create again the unit manager, and we submit the pilot we have created to the unit manager. If you're using more than one pilot, you submit all those pilots from what this instruction has returned to the pilot manager, and it knows that it can submit units to more pilots. So since we're doing a chain, we have, first of all, we need to describe all the tasks from the first level. That's the set A, and this is what this for loop does. Actually, it creates a description of those tasks. We set up in the environment that the CU list, the CU set that this compute unit is going to exist as A, and its number. I'm going to change the executable in a while, and its arguments, and then the number of cores. We submit those units on the unit manager, and we don't wait for them actually to execute, but we start describing the units of set B while waiting for each specific unit from set A to finish. So in this while loop, for every unit in set A, we check its state, and actually we wait for that specific unit to be executed. And as soon as it's done, we create the unit description for set B, and we submit that to the unit manager in order to start execute the second set. And then after all units from set A are finished, we're waiting for all units from set B to finish. And at the end of course, we close the session of the pilot in order to close it and finish the execution. So I'm going to come up here. I assume that you did your changes. I'm going also to do my changes. Pilot course 2. Number of chains, I'm going to say 4 chains in total. As we said, in the instructions, it's a bin echo for both of them. Let's make sure I didn't make a mistake. Yes, and I'm not changing the queue because I'm not going to run it locally. And if you wanted to run remotely, you should add pdesk.project equals your allocation number. Save it and do Python chain tasks.py, I think, yes, and should start running. As you can see, as soon as a compute unit from set A finished, it submitted a compute unit from set B. And then at the end, we waited for all the compute units from set A, from set B to finish. They have the same number, the units from set B have the same number as the respective unit from set A. And then after everything was finished, we closed the session and the execution was done. The third example, that exercise that I wanted to show you, is mainly about couple tasks. So couple tasks is we have a set of tasks, set A and set B of tasks that we're going to execute in parallel, and when that is finished, we want to start submitting another set of tasks C. This example tries to show you how synchronization can happen inside the pilot and how to create dependencies between compute units, and also how you can have an execution that is that can vary in size. The file is called coupletasks.py. It also has similar changes that are needed to be done. In case you're using a resource, I would suggest to set up the cores of the compute units to a number different than 1. It's going to show you how things are going to be executed. And also in line 70, add your project description for the resource you're using. Again, the changes that you may need to do are on the top of the file. I'm going to wait some time and then go through it again. I'm going to make the changes my script as well. Hope everybody had enough time to finish it. So localhost pilot course, I'm going to increase them to 4. Number of couples, say 4. Now our first compute unit is going to take 2 calls. Compute units from set B are going to take 1 core each, and the compute units from set 3 are going to take 3 core seats. I'm not using a queue because still it's localhost. As I said in all 3 previous examples, we create the session, we create a pilot manager based on that session. Then we do the description of the pilot, submit the pilot description to the pilot manager, create a unit manager, add the pilot to the unit manager, and then we start creating the compute units that we want to execute. Now, in this for loop, we create the units from set A, and we just append them to a list, and then that list is being submitted to the unit manager. If we don't use the wait units blocking command, we can create. Our script will continue executing, and in this case, we're creating a second set of compute units that are going to be executed in parallel with set A, and then we submit those in the unit manager. Now, at this point, we block the execution of our script. So while the units from set A and set B haven't finished, the script will not continue. And as soon as they're all done, we create the description for units set 3, which are then submitted to the unit manager. And we wait for those to finish. And as usual, at the end, we close our session. So let me go up and do the change. I've done them already. Okay. And if I do Python coupled .py, as you can see, we have registered the pilot with a unit manager. We've created set A, we've created set B, and now we wait for those 8 units to finish executing. They're done. Units from C are submitted and done, and the session is being closed. Also, in this tutorial wiki page, we have an example for the others for Ensemble-Toolkit, which because of mainly due to time constraints, I'm not going to go through it. You're welcome to open tickets, ask, send, or communicate with us through Slack with any questions. And now, if you would like to go to a discussion with questions and comments, that would be great. Which can be directed, to both of us, Professor Zhao.
All right. Thank you, Anis. Thank you, Professor Shantanu. We might wait for a few questions, but while we wait, I'd like to ask a question myself. So, how do RADICAL-Cybertools handle failures of like tasks, of pilots? Maybe can Radical pilot fail at some point? So, and another like related question, what if, so I understand that various things might happen on their supercomputer where people might want to use RADICAL-Cybertools. How should people handle login nodes failures? For example, if they start the job on a login node and it fails, is there any backup plan or something like that?
So for your first question, where a unit fails, you see that on the execution. There is no fault tolerance right now on Radical Pilot. It's been created, but the user can check the state of the unit when that finishes, and if it fails, can submit the unit to the unit manager, and it's going to be executed again. In case a pilot fails, it either gets dropped out of the session the session knows whether a pilot is active on the state of the pilot. If it's a single pilot session, then the session closes all on itself. Thank you for the third question. I forgot to mention something. The pilot scripts are not launched from the login node. They are launched specifically from the user's laptop, and then through Saga we submit a job script on the scheduler of the research. Now, if for some reason the state of the pilot is being lost, Radical Pilot understands that and closes the session with a failure. As soon as our Radical Pilot is active, there is no communication through the login node. The client machine communicates directly with the compute node that the pilot is active, is running.
All right. Thank you very much. I'll ask one more question, which is like bothers me a little bit. So there is it looks like there is at least some learning curve. Do you provide any sample scripts for users to peek at and maybe reuse, modify, or do you want them to learn the actual syntax, Python syntax that Radical Pilot module
all
enables?
The examples, I see what you're saying. All the examples I showed right now are fully documented on the documentation. They're also part of the GitHub repository of Radical Pilot. A user can download them, change them as they like, use them. Everything is open source, so you can do whatever you want with them.
All right, thank you so much. Thank you very much. It was a very interesting presentation. So right now I'd like us to see the final slide. Yes, so there will be no webinar on May 17th, which is next week. Our next webinars, planned webinars, will be first one on May 24 by Mats Ringe, and it's titled Pegasus Workflow Management System. And after that, we have a webinar on May 31st by Jason Larkin, and this webinar is titled Automated Code Generation with Spiral. We'll be sending you a quick 5-question survey after the webinar, and we ask you to complete this so that we can improve the webinars further. I encourage all the participants who watch this webinar live or after the fact to please use Slack channel to ask presenters questions, because this is a way for you to interact with them directly. With that, I'd like to thank everybody, all the participants and presenters for the great presentation, and we'll see you in 2 weeks. Thank you.
Thank you.